In this video, we're going to talk about electronegativity and polarity. We're going to talk about what is electronegativity, what is polarity, and discuss that within a covalent bond. We're then going to talk about examples of polar molecules and non-polar molecules. Now, electronegativity and polarity only occur within covalent bonds, so it's useful to know what that is and make sure you know the definition. The definition is electrostatic attraction between a shared pair of electrons and positive nuclei, which is really good that you make sure is part of your definitions that you recall. Now, in a covalent bond, atoms are held together, and they're held together by the nuclei's attraction for the electrons that are shared. So if you look here, this diagram, this pair of electrons here is attracted to the nucleus in here and the nucleus in the other hydrogen, therefore holding it in place. Why are some bonds polar? So that is because the shared pair of electrons are closer to one nucleus than the other. And there are two main reasons why they would be closer to one nucleus than the other. And that's because the atoms are of different sizes. And you can see in this diagram here we've made a massive atom like this. And you can see that the nucleus is in the centre, and the distance between the nucleus and this pair of electrons is massive. Okay? And it's massive compared to this tiny distance on this small atom next to it. So if the shared electrons are closer to one atom than the other, that's going to be a polar bond, and we'll go into more detail about that soon. The other one is if you have a different nuclear charge. A nuclear charge is just the number of protons in the nucleus. So if we look at two atoms here and we say one's got 5 protons in the nucleus and the other one's got 7, well, those 7 protons are going to pull those electrons just a tiny bit more towards them than the one with 5. If we carry on to electronegativity, electronegativity is essentially the attraction of a bonded atom for the pair of electrons in a covalent bond. So if, for example, as we did in the last slide, an atom is smaller, it has a higher nuclear charge, it will be electronegative because it will pull the electrons towards itself. And that's within a covalent bond. Again, required definition. Now, this uneven attraction means that you can get a dipole. And let's go into detail what a dipole is. Now, a permanent dipole is one where you have an electronegative element and a non-electronegative element. So here we have hydrogen, and hydrogen is not very electronegative, and fluorine is very electronegative. Fluorine is smaller than most atoms, and it has a high nuclear charge compared to most atoms. Okay, and so with that, the pair of electrons goes slightly closer to the fluorine because it's more electronegative. Because of that, this end is negative. Okay, it's just a slight negative, tiny bit negative, and that is denoted by delta plus, and you'll draw delta lots during your A-levels. So delta plus says a little bit negative that end, a little bit positive that end. That's because the electrons have gone that end, so this is missing some electrons, making it slightly more positive. That permanent dipole, okay, gives a polar bond. So that's what we mean by polar, the fact it has a dipole. And the fact it has a plus and a minus means it has a dipole. So this is a polar bond with a dipole. Electronegativity values. Now, you can tell which ones are electronegative, which elements are electronegative, because of these high electronegativity values. So F typically has a high electronegativity value, C is much lower. So this CF bond would be polar. You can actually look at these values here. So we've got some electronegativity values, and these just say how much do these atoms attract a bonded pair of electrons in a covalent bond. So these, NOF or NOF, attract a pair of electrons in a covalent bond and pull them towards themselves. So if any one of NO or F is bonded to C, it will be polar, there will be delta minus and delta plus. The opposite of that is a carbon-hydrogen bond. A carbon-hydrogen bond, the values are similar, therefore the bond is non-polar. Neither of the atoms are pulling the electrons towards themselves. Now, where does this go in terms of electronegativity values for a lot of substances? So it tends to be that the metals and the atoms on the left-hand side of the periodic table have very low electronegativities. They don't have any. So any kind of strong electronegativity that means they pull electrons towards themselves. They tend to lose electrons. So if we go over here and we go to the right-hand side of the periodic table, this is not the whole periodic table, but it's just a section. And you can see that NO or F and ClBr Now these are the most electronegative elements. And if you have a periodic table in front of you, just put an arrow on it going up to the top, and all the electronegative elements are in like an arrowhead, and we'll show you now. So N, O and F are the most electronegative, 3.3, 3.5 and 4. And then we have Cl and Br, which are very close, just slightly below with 2.8. But can you see that's like an arrowhead? And so the most electronegative elements are Nof, Clobra. So I refer to it as Nof, Clobra, because the green ones are slightly less electronegative than the yellow ones. Even though chlorine and nitrogen are roughly the same, there will be different types of intermolecular force with Cl and Br as there is with NaOF because of that fact. So let's look at some examples so we can recognise those dipoles. Oxygen. Now oxygen is the same element, so it's literally just, okay, so there is your oxygen. And if you look, both of the elements are exactly the same, and therefore the electrons are going to be in the middle because they're both pulling with exactly the same electronegativity. So there is therefore no dipole at all. Electronegativities are the same. We then go for ammonia. Now if you look at ammonia, ammonia is here, so that's NH3. We have a lone pair of electrons on the top there, if we're drawing that properly. Okay. Now remember, Nof, Clobra. So basically all the electronegative elements are in Nof, Clobra. N is in Nof, Clobra. Therefore that is more electronegative than the other elements here, which is hydrogen. So therefore we will have that as delta negative. Okay, so that is delta negative. If that's the case, that is delta positive. That means all of them are delta positive because they're all connected to the nitrogen. So we have a dipole. This is polar. Okay. Next one is water. So water, again, has two lone pairs. Okay, so two lone pairs, and is in Nof, Clobra, N-O. Okay, so therefore this is going to be delta negative, delta positive, delta positive. Okay, so we have polarity here again. That means on both of these, the electrons will just be that little bit closer to the nitrogen in this case, and a little bit closer to the oxygen in this case, which is why you get a dipole. Okay, and the last thing to mention is the fact that because of these lone pairs, they're not symmetrical, any of these. Okay, because they're not symmetrical, the dipoles don't cancel. Okay, and that's an important thing. N, O, F, Cl, Br, Nof, Clobra have higher electronegativities than other elements, and in these molecules, they're not symmetrical. So therefore, these are polar, and they have dipoles. So we've looked at examples where you have the same element, therefore there is no dipole, and where you have different elements and some with a higher electronegativity and no symmetry, so therefore they have a dipole. Let's look at some that have symmetry. So carbon dioxide, okay, is, and you can see this should have some form of overall dipole. That's because Nof, Clobra, as in oxygen, is electronegative, and so basically it's pulling the electrons that way and pulling the electrons that way. But because it pulls opposite directions, it is cancelling out overall, and there is symmetry down the molecule. So you generally just look, if there's symmetry down the molecule, the dipoles cancel. So if we look at our next example, carbon tetrachloride, this is very simple to see the symmetry, and the dipoles would therefore cancel. But what if you had carbon tetrachloride? So if we look at carbon tetrachloride as a 3D diagram, okay, and there you have carbon tetrachloride. There's no lone pairs. Everything is pointing in opposite directions to each other, essentially. There's symmetry all the way around the molecule. This is tetrahedral, 109.5. This is linear, 180. If it's tetrahedral and you've got the same element on each one, then there is symmetry down the entire molecule, and therefore it will not have a dipole. Okay, so it's really important that you realise that if you have something that is symmetrical, and that means it has, for example, the same element pulling in opposite directions in the molecule, even though you should have a dipole because this is chlorine NOF clubber, this is oxygen NOF, okay, that's electronegative, that's electronegative. Even though that's the case, if it's symmetrical, the dipoles cancel each other out. So these have no overall dipole and therefore will be considered as non-polar.